So based on the process of how to find the derivative of inverse trigonometric function that we saw for sine inverse, here is the list of all the standard functions and their derivatives. So as we have seen, derivative of sine inverse x is 1 upon root of 1 minus x square, where mod x is less than 1. That means x has to be numerically less than 1. Now for cos inverse x, you will see that it's almost the same term as sine inverse x, except that it is negative. So you attach the negative sign to it. And once again, the restriction on x is same, that is mod x should be less than 1. For tan inverse and cot inverse also, you will see that the terms are just opposites of each other. For tan inverse, it is 1 upon x square plus 1, whereas cot inverse has minus 1 upon x square plus 1 as the derivative. And we know that for both of these functions, the x can be any real number. So that is the domain of those functions. Moving on, we have the remaining two, that is sec inverse and cosec inverse. Once again, here also you'll see that in the formula, the only difference is of the sign. For sec inverse, we have 1 upon x into root of x square minus 1, whereas for cosec inverse, it is a negative of the previous one. And as we know, in both of these, the domain is that mod x should be greater than 1. That is, x should be either bigger than 1 or smaller than minus 1. Alright, so we have to use these as standard formulae in solving the sums. Now apart from this, there are some standard shortcuts, or rather the substitutions, which we need to use so that the differentiation of inverse functions gets very much simplified. So let us see what are those substitutions that we often need to use. So here is the list of them. We will see couple of patterns and what substitution will work for that. Let's consider the first pattern, that is root of a square minus x square. Okay. Now in this case, we put x as either a sine theta or a cos theta. Now let's understand why this substitution and how it works. Okay. So if you look at this particular pattern, and let us try to substitute x equal to a sine theta, say for example. So therefore, root of a square minus x square will become root of a square minus a square sine square theta, correct? So therefore, that gives us, taking a square common, we have 1 minus sine square theta. And we know that 1 minus sine square theta is cos square theta. So we have square root of a square cos square theta, which is nothing but simply a cos theta. So you see, a complicated looking expression gets simplified to a very simple expression which we can easily differentiate. Of course, at the end, what we have to do is, since theta is the variable which we brought on our own for the sake of substitution, at the end we must replace it with the corresponding inverse function. So what is that? That is, if say we put x as a sine theta, so that means sine theta is nothing but x by a. So therefore theta is nothing but sine inverse of x by a. So therefore here theta is nothing but sine inverse of x by a. Right? So similarly, we have to do the substitutions as mentioned here and then use them in the examples. Right? All these substitutions are basically coming from the standard trigonometric identities, as we know. So whether it is basic square identities, that is first, second and third, or maybe double angle formulae or triple angle formulae and so on. So we'll see all these patterns basically come from those identities. So for example, let us look at the last three. We have to ask the question, where do we see this particular pattern in trigonometric identity, that is 1 minus 2 into something squared, right? So here if we put that x as sine theta, we will get 1 minus 2 sine square theta, and we know that this is nothing but the double angle formula of cos, that is cos 2 theta. So therefore, putting this particular substitution, we get a simple term which is easy to differentiate. Alright. So based on this we will solve few sums now.